Hello and welcome to lesson 7.9. More hidden identities. Okay, let's kind of jump in. So, let me make sure my mic is on. Yep, the mic is on. Okay, so in the diagram, the three complex numbers have been graphed as vectors. Okay, talking about vectors now. Rewrite each complex number as a point in the form a comma b. So this is pretty straightforward. This is -3, this is 4, okay? So this is your A, this is your B, okay? That's kind of it. So this is 5, this is 2, and then this is 1, and this is -6, okay? So graph the complex numbers as vectors on the diagram. So we're simply going to be graphing these. So at -5, we go to -5, we go down 3 units, and then we should be able to kind of draw our vector. Oh my goodness. So pretend this is perfect. And we should draw a little flechita, a little arrow. Okay. Pretend you can see. So okay. So this is my stopping point, and then this is my arrow. Okay. And then we'll call that A. Then let's do B at 2, and then plus 4i. So this is right there. So that's my terminal um, point, and then my vector. Oh my goodness, should look something like that. This is fine. This is B, and then we're talking about -6 plus I. So there's an imaginary 1 here. So you go to -6 and then up 1. So it should look something like this. Oh my goodness, something like that. Okay. Um, Little arrow, and then let's see, and then let's do D in red. So 2 minus I. So this is a 2 minus I. It's right there, and perfect. Great. Okay. Now we're talking about the magnitude of a complex. Oh, was I supposed to draw those? Oh my god. Okay, so I drew those in the wrong place. Um, Maybe I can just like, I'm gonna copy those and just let's see how this works. Paste them. Okay, let's pretend that that's perfect. Cool. The magnitude of the complex is its modulus. It is symbolized by the notation absolute value of a plus bi, but it doesn't actually mean absolute value, right? So where this just means the magnitude of it, so you take the square root of a squared plus b squared. So again, I'm gonna kind of jump through some of these pretty fast. This is equal to just um, -3 squared plus 4 squared. So this is just going to be equal square root of 25, which is equal to 5, okay? This is going to be equal to 25 plus 4, which is equal to square root of 29. This right here is equal to 1 plus 36, which is equal to square root of 37. This is equal to 25 plus 9, which is square root of 34. This right here is equal to square root of 4 plus 16, which is equal to square root of 20. And then we're left with square root of 36 plus 1 is equal to square root of 37. And then last but not least, we're left with 4 plus 1 is equal to square root of 5. Okay, perfect. Solve the following trigonometric equations. Okay, write the answers in the form theta plus 2 pi k, where 2 pi represents the interval between successive solutions and k is any integer. Okay. So yes, we're going to be doing a lot of solving now. I have some pages added already, but let's kind of go through these. These I will go in detail. I think these are pretty fundamental for not just Algebra 2, but for pre-calculus and calculus and so on. Okay, so again, we're solving these equations just like we would any other equation, right? So I'm gonna isolate what I want my x variable, right? So I'm gonna move my square root of 2, move that. So I'm left with 5 cosine x is equal to 0. And I'm gonna divide by 5, right? So then cosine of x is just equal to 0. And then once I'm here, I have to take cosine inverse of both sides to isolate my x. So x is equal to cosine inverse of 0. We should kind of think about what does that mean for us? What is my x value? I can't just leave my x value like that. So I'm gonna start drawing my unit circle because all of this goes back to working with your unit circle. I'm gonna do rough sketches from the unit circle for most of these problems. Okay. So cosine is my x, right? So when is my x 0? So my x is only 0. Oops. My x is 0 up here and then down here again, right? So x here is equal to, this happens at pi over 2. So at pi over 2 plus k pi or pi k and plus or minus, right? So what I mean by that is that this is 3 pi over 2 and it's going to keep on going, right? Because it's a cycle. It keeps on repeating itself and it touches these two all the time. So you could have written your answer as x is equal to pi over 2 plus or minus 2 pi k, and then x is equal to 3 pi over 2 plus and minus 2 pi k. But that to some extent is a little, I want to say, redundant. Sure, we can use that because this kind of encapsulates them all together. Yeah, okay. Let's talk about 6. So that was 6. Let's talk about 7. Let's talk about you. Nope. And then we talk about 7, right? Okay. So again, I want to isolate my my x variable, right? So you want to isolate, move everything to one side. So I left with 2 sine of x is equal to negative square root of 2. And then let's divide this by 2 on both sides. So I'm left with sine of x is equal to negative square root 2 over 2. Okay. Now let's take sine inverse. Sine inverse, what I do to one side, I do to the other. Negative square root 2 over 2. Okay, now you have to think about what x values, so what values in my unit circle give me that it's sine, sorry, what x values give me negative square root 2 over 2. What y, well, when is sine equal to that, right? So we should know that sine is negative in quadrants 2 and 3, right? And this should know that it's here and here. So this is 1, 2, 3, 4. Oh, sorry, that's wrong. This is 1, 2, 3, 4, 5 at 5 pi over 4, 6, 7, 7 pi over 4. So those are two different values. So then x here is equal to 5 pi over 4 plus or minus 2 pi k, right? Because it's going to take me on one whole rotation to end up being there. And x is equal to 7 pi over 4 plus minus 2 pi k. Now in this case, there's actually no way to kind of solidify your answers. I mean, there is, but I'm not going to talk about that just because it's not as straightforward as number 6 was, right? Because here I was adding plus pi k. So to get from here to here, I add what? I add like pi over 5 pi over 4 plus 2 pi over 4 equals 7 pi over 4. So this is pi over 2. But then if I add pi over 2 again, I would end up somewhere over here, which is not part of your solution, right? So it's just, these are two different things, okay? Well, let's talk about 8. So going to number 8. Again, I want to isolate my trig expression. So I'm left with tangent of x is equal to subtracting this. I'm just left with square root 3. That's it, right? So now I need to do tan inverse. So x is equal to tan inverse of square root 3. Now this one's not as common, right? So we have to think about our unit circle a little bit. Think about what tangent is. Tangent is sine over cosine. So when is sine over cosine equal to square root 3? So there's going to be one location either at pi over 6 or at pi over 3. And off the top of my head, I'm going to kind of show you what it actually is and where it actually does that. So this is my x is 1/2. This is square root 3 over 2. And this is the opposite, right? Square root 3 over 2 comma 1/2. So tangent over here, the tangent here is equal to square root 3 over 2 times 2 over 1, which is square root 3. And then tangent here is equal to 1/2 times 2 square root 3, which is equal to 1 over square root 3. So then we know that it has to be pi over 3, right? So then x is equal to pi over 3. But where else does it happen? So tangent is square root 3 over here as well. So like technically diagonally from here, right? You should be a little familiar with the way the unit circle works and realize that tangent is positive here and then positive here. So that's how many units did you add to get over here? What value is this anyways? So this is pi over 3. So we should be going to 1, 2, 3, 4, 5, 6, 7, 8 pi over 6, which is 4 pi over 3. So to get to from pi over 3 plus what number gives me 4 pi over 3? So this should be a 3 pi, right? So this is plus or minus pi k or k pi. Okay, so those three were pretty straightforward. Highlighting my answers for x. So here we go. Now the next ones will become a little bit more challenging, I would say. So please bear with me. Yes. Okay. So 9. Okay. So my first instinct here, I want to have everything to one side just because that's kind of where my brain has always taken me to, right? You want to have set everything equal to 0 because this is an equation. So I'm left with 0 is equal to, let's do 3 cosine squared of x minus sine squared of x. Okay, now this one, it's like, okay, what do I do next? What can I even do? What, like, you know what I mean? Like, what is it? I have cosine squared, I have a sine squared. So you have to really dig into that toolbox of like identities and kind of figure out where can you combine these? What identities have you learned? So the one that should really come to your mind is sine squared of x plus cosine squared of x equals to 1. And now I'm gonna do and solve for sine squared of x. So then sine squared of x is equal to 1 minus cosine squared of x. Okay, and you could have solved for cosine squared of x. I'm choosing not to do that, but now I know that what this is, and it's all in terms of cosine, right? So I can plug it in here. So I'm left with 0 is equal to 3 cosine squared of x minus, to be careful here, parentheses, this entire thing, 1 minus cosine squared of x. Okay. Now let's kind of just clean this up a bit. This is 3 cosine squared of x minus 1. Distribute the negative, so plus cosine squared of x, right? So cleaning this up even more, 0 is equal to 4 cosine squared of x, combine those like terms, minus 1. Now, this is a lot simpler, right? I can start solving now. So move stuff to one side. So 1 is equal to 4 cosine squared of x. 1/4 is equal to cosine squared of x. Now I'm at this point where what can I do next? So you can take the square root, right? You bring the square root, and what comes along with the square root? A plus and minus, right? So I'm left plus and minus. 1/2 is equal to cosine of x. Now, what can I do next? What should I do next? How do I get x by itself? So I have to take cosine inverse. What I do to one side, I do to the other. So I'm left with x is equal to cosine inverse of plus and minus 1/2. So let's go to my unit circle. I'm drawing a rough sketch of it. So this is my unit circle. Great, cool. So I'm looking for locations of when cosine is plus or minus 1/2. So that's going to happen here. This is 1 point. It's going to happen here, here, and then here. So what are my angles for that? What is my x values for this? So what angle is this right here? So this happens at pi over 3. Pi over 3. So this is 1, 2, 3, 4. So at 4 pi over 6, which is 2 pi over 3, 4, 5, 6, 7, 8. So 4 pi over 3, 9, 10, and then 5 pi over 3. So those are my x values, right? Okay. Now, let's kind of think about this because there's different ways to write them. So x is equal to, let's think about this, pi over 3 plus 2 pi k. X is equal to 2 pi over 3 plus 2 pi k. X is equal to 4 pi over 3 plus 2 pi k. And x is equal to 5 pi over 3 plus 2 pi k. So those are acceptable ways of writing your solutions. I would say, however, we might ask you to kind of like write them down in a simpler form, because you see that a lot of these will be redundant, right? Like, for example, is there a way that I can combine these two within the same equation? Think about that. Because all of these points are solutions to this, right? Because I'm taking cosine inverse of plus and minus 1/2. So let's think about that. So if I just keep x is equal to pi over 3 plus and minus what? So from pi over 3, how do I get down to 4 pi over 3? I add what? Pi. So plus pi k. And x is equal to 2 pi over 3 plus and minus what? Pi k, right? So these two are kind of what I would rather you write as your solutions, and you should be able to kind of recognize those. Yeah, okay. Now some of you might think a little bit more ahead, right? And think that, is there a way to write these using only one solution, right? So we see that from pi over 3 to 2 pi over 3, how much do you add there? Just pi over 3, right? But then from here to here, how much do you have to add? Right? Not just pi over 3. So you have to be careful there, and I think that this is kind of the best way for you to write those solutions. I'm not going to get into writing it the other way, just because of timing. Yeah. And how can you check your work? So let's kind of just say that k here was equal to 1. So then I'm left with x is, if k is equal to 1, let's do it here. So if k is equal to 1, I'm left with pi over 3 plus pi over 1, right? So let's kind of call that 3 pi over 3, which is equal to 4 pi over 3, which is the solution that we know and love, right? Good. So that's kind of how you know. And then here you can say that this is 2 pi over 3 plus 3 pi over 3, which is 5 pi. 5 pi over 3, which is another solution that we know and love, right? Okay. That's how I want you to do that one. Let's talk about 10. 10. I have some space here. Good. Let's see. Okay. So let's kind of change up our colors. I'm getting tired of that. Let's go back. Okay. So again, very similar. I want to move everything to one side. So if I do that, I'm going to get this is equal to negative, so 1 minus 2 minus 2, right? So negative 1 plus sine squared of x plus cosine of x. Okay, so again, I kind of at this point where like what can I combine, what can I not combine? And sine squared of x from our Pythagorean identity is equal to 1 minus cosine squared of x. So maybe that will help us. So this becomes negative 1 plus 1 minus cosine squared of x plus cosine of x. At this point, I'm just doing some trial and error technically. But is this going to help us, right? So negative 1 plus 1 goes away, so that goes away. And I'm left with negative cosine squared of x plus cosine of x. This is equal to 0, okay? And now let's factor something, right? So they have a cosine in common. So this can be cosine of x. And let's write this as 1 minus cosine of x. Yep, this is equal to 0, right? So that looks fair. And now we know that we can easily, well, no, not easily, right? But we can identify that we need to set each of them equal to 0. So cosine of x equals to 0 is my first one. So then I cosine inverse, x is equal to, again, doing a really rough sketch of my unit circle. X is equal to 0, where? Up here, and then here again. So we've seen that solution before. It's pi over 2 plus and minus pi k. Now we're left with my other part. So this is 1 minus cosine of x equals to 0. 1 is equal to cosine of x. Then we take our cosine inverse of both sides. So x is equal to cosine inverse of 1. So where is x equal to 1? Cosine is equal to 1 here, right? That's the only location. So then x is equal to 0 plus and minus 2 pi k, or just plus and minus 2 pi k, okay? So let me make sure that I'm highlighting these solutions. So this is this and this, right? Those are your two valid solutions for this, okay? Let's go to 11. So 11, you should be able to kind of recognize that this is a trinomial, so you can write it as a product of two binomials, right? There's going to be some factoring going on here. So this is 2 sine of x, open parentheses, sine of x here, okay? And now you need numbers that multiply to positive 1, which can literally only be 1 and 1, and add up to 3. So plus 1 doesn't really matter, right? Equals to 0. You can double check your work by distributing this out. But this is valid, right? You end up getting 3 sine of x as your middle term. And now this goes back to kind of what we've been doing, right? Except now we have a trigonometric function, sine. You set each of these, you set them equal to what? You set it equal to 0, and then you start solving. So I'm left with 2 sine of x plus 1 equals to 0, and then sine of x plus 1 equals to 0. Let's kind of take it one by one. So here I'm subtracting 1 minus 1. So I'm left 2 sine of x equals to negative 1. Let's divide this by 2. So then sine of x is equal to negative 1/2. Okay? Now you want to take sine inverse. Sine inverse. So then x is equal to sine inverse of negative 1/2. So again, doing a really rough sketch of my unit circle. Where is sine equal to negative 1/2? So you should pick up on the fact that sine is only negative in these bottom quadrants. So it's going to be right there and right there. So what values is that? What values are those? So I'm going to count. So this is 1 pi over 6, 2 pi over 6, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. 7 pi over 6, 8 pi, 9 pi, 10 pi, and 11 pi over 6. Okay, so then x here is equal to 7 pi over 6 plus or minus 2 pi k, and x is equal to 11 pi over 6 plus and minus 2 pi k. Now I'm not done, right? I have a whole other solution here. So I have sine of x is equal to negative 1. Take sine inverse. Oops, what's going on? X is equal to sine inverse of 1. So when is sine equal to 1? Sorry, negative 1. This is negative 1, negative 1, negative 1. It's negative 1 is down here at 3 pi over 2. So x is equal to 3 pi over 2 plus and minus 2 pi k. Okay, so these are my solutions here. Why is it 2 plus 2 pi k? Because remember, this is going to keep on going in circles and circles and circles and circles forever and ever and ever, right? So sine functions have that property. So if it was 7 pi over 6, you would get something that's equivalent to negative 1/2 if you go 1 full rotation. 1 full rotation is 2 pi. Here, k means it's an integer. Okay, that's all it means. Let's talk about 12 now. Okay, so 12 looks pretty straightforward, right? So let's kind of start dividing this by 2, divided by 2. So I'm left with sine squared of 2x is equal to 1/2. And now what do I get? What do I need to do to get rid of the sine squared? I take the square root, right? What do I do to one side? I do to the other. So that gets rid of the sine squared. So now I'm left with sine of 2x, which is equal to plus minus square root of 1/2. Now let's take some time here to kind of analyze what square root of 1/2 is. So plus and minus square root of 1/2 is equal to plus and minus square root of 1 over square root of 2, which is equal to just 1 over square root of 2, right? Now we can rationalize this. When you rationalize this, you multiply the top and the bottom by square root of 2, right? So then you should be pretty familiar with that, and that's equal to plus and minus square root 2 over 2. Square root 2 over 2. Okay? Now, we're not done yet, right? That's just part of the process. We need to take a sine inverse. Sine inverse. So then you get 2x is equal to sine inverse of square root 2 over 2, plus and minus. Okay? So going back to my unit circle, I'm doing a rough sketch of this. As I'm looking for specific locations. I'm looking where sine is plus or minus square root 2 over 2. So you should be familiar with that. It's going to be right there, there, right there, and right there, right? So this is at pi over 4. This is at 3 pi over 4, 5 pi over 4, and then 7 pi over 4. Okay? So this one's a special one because this does happen every what? What happens? Every single one of these happens every what? So from pi over 4 plus what gives you 3 pi over 4 plus 2 pi over 4, right? Now you're at 3 pi over 4 plus what value gives me 5 pi over 4? 2 pi over 4, right? So it's every 2 pi. So then 2x here is equal to pi over 4 plus and minus what? Pi over 2 k. Now I'm not done. Why am I not done? Because I need to take care of the what? Of this 2. So I'm going to divide this by 2, which is the same thing as multiplying by 1/2. So multiply everything by 1/2. So x is, I'm left with pi over 8 plus and minus pi over 4 k. Okay, good. This was a pretty interesting one. I like this one. Let's change up our colors. Okay, now we're talking about 13. Again, you want to move everything to one side and set everything equal to 0. That's kind of your best friend, right? That's the best way to do this. So I'm left with 2 cosine squared of x minus cosine of x minus 1 equals 0. Okay, now you have a trinomial now, right? So what can you think about doing? Think about what we've done in the past. We did it already. We did it for number 11. You have a trinomial. You want to make sure that you break this down into a product of binomials. So this is 2 cosine of x, cosine of x. Okay. Now I need numbers that multiply to -1. So, and add up to -1 here, right? So then one of them has to be a plus, one of them has to be a minus. So this is going to be -1 here and a +1 here. Okay, double check your work. So 2 cosine squared makes sense. Minus 2 cosine plus 1 cosine is going to be negative cosine minus 1. Okay, so far all we're doing is essentially factoring, right? Okay, now the rest comes as follows. You set everything equal to 0. So you set each of them equals to 0, and then you solve, right? So then I'm left with 2 cosine x is equal to -1. So then I'm left with cosine of x is -1/2. Now you take cosine inverse, right? We've done this. X is equal to cosine inverse of -1/2. Okay, so now I'm going to move this a little bit to the side, and then I'm going to draw my little unit circle, a rough sketch. And I encourage you to always do a rough sketch of unit circle, right? Unless we give it to you, which I'm not sure will be given to you because you were honors class. I could be wrong. However, it's important to kind of know, right? So a -1/2 cosine is negative only at quadrants 2 and quadrants 3. And that location is going to be, let's make it more clear, here. And I'm just doing a rough sketch, right? I'm not saying that that's exactly where, but in my head, I can visualize that it's there, right? So what location is that? So this is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, which is 2 pi over 3, 4, 5, 6, 7, 8. So 8 pi over 6, which is 4 pi over 3. So then I'm left with x equal to 2 pi, that's a horrible pi, 2 pi over 3 plus or minus 2 pi k. Did I been writing plus or minus? Yeah. And then x is also equal to 4 pi over 3 plus and minus 2 pi k. Okay. I'm not done though, because I have another solution, right? Cosine of x minus 1 equals 0. I add 1. And then this one we should know and love, right? So then x is equal to cosine inverse of 1. So then x happens. 1 is cosine 1. X is cosine 1. Cosine is 1 here. At 0, plus and minus what? 1 full circle. Another full circle. 2 pi k. Right? So x can just simply be written as plus and minus 2 pi k, where k is an integer. Okay? You have those, bum, and bum. Okay? Yes. Okay, perfect. Okay, let's erase this so you don't see this, even though you already saw it, right? Okay. Same thing here. So 14. 14 looks like it's going to be what? It's a trinomial. We want to factor it, right? That's kind of what your first instinct should be about. So it's 2 cosine x, and these have been pretty relatively straightforward. Let's see about this one. So I want numbers that multiply to 2, so it's just 1 and 2. So there has to be a 1 and a 2 somewhere there. And how do you know which one goes which? So this is a -5. So you should kind of pick up on the fact that the one that has a negative should be the one that is being multiplied to this 2. And why is that? Because you're going to get, oh, actually, no, that's not even right. This would become a -2, so you need to make this a negative. So both of them have negatives, but the one that is getting multiplied with the 2 is the one that should be the greater number, right? Because this becomes -4x minus 1x, which is -5 cosine x, right? That's kind of what we want. Equal to 0. Okay. And then the rest, we just solve it. So 2 cosine x minus 1 is equal to 0. So then 2 cosine x equals to 1. Cosine x is equal to 1/2. And I'm going to do cosine inverse. Cosine inverse. X is equal to cosine inverse of 1/2. Now let's kind of think about our unit circle. When you think about the unit circle, that darn unit circle, right? It always comes back to it. So where is cosine equivalent to 1/2? So that's going to be here and here. A rough sketch, right? So what value is this? This is pi over 3. So let me count. I don't know it off the top of my head, but I know that this is 1 pi over 6, 2 pi over 6, 3, 4, 6, 7, 8, 9, 10 pi over 6, which is 5 pi over 3. So I'm left with x is equal to pi over 3 plus and minus 2 pi k, right? And x is equal to 5 pi over 3 plus and minus 2 pi k. So those are my other ones. And then last but not least, I set this last equation equal to 0. So cosine x minus 2 equals 0. I add 2. So I'm left with cosine of x is equal to 2. Cosine inverse. I'm carrying this out just like I would any other problem. X is equal to cosine inverse of 2. Is this ever a thing? Is this ever possible? No. So there's no solution for this because the domain of cosine, sorry, not the domain, but the range of cosine is from a -1 to +1, right? So nothing will ever equal this, okay? So my only solutions here are these, okay? You can double check that cosine, so let's do cosine inverse of 2. No real answer. Like there's no such thing. Okay. Now I do want you to realize that I didn't use a single calculator for any of these problems. And you shouldn't really need to use a calculator for any of them. Okay. You could graph your you could graph these and then solve and then like kind of see where it intersects. But I just don't think that the TI is a good calculator for this. So let's maybe do just one. Let's do one on Desmos. Let's see. Let's see how it works. Okay, so let's do a graphing calculator. And let's just graph. Let's do number 12. So we have 2 times, there's no sine. Sine of 2x, close up parentheses, squared. Okay, that's my first one. And then I set this equal to 1. Why doesn't it graph it? Okay, maybe set y equals 1. Okay, cool. So we see that the solutions here should be exactly where? The solution should be each of these intersections. So what's the first one we have? Pi over 8. That's x. Did we get that? we got pi over 8, okay? So that's my first one. Now, what was my next one? 5 pi over 8. So how do you know if you're right? So let's kind of just quickly go here. So pi over 8 plus and minus pi over 4 times 2. Let's just say my k integer is my, I don't think this actually means it's your second solution, but it just means that if you were to put in a number 2 for k, then this would give you a solution, right? So this is pi over 8 plus and minus 2 pi over 4, which let's add fractions. So this becomes 8 and 4, which is equal to 5 pi over 8, which is exactly that solution. And then the minus 1 would be a negative 3 pi over 8, right? So you're definitely able to check your work using Desmos. Okay, you can check your work, and those are the ones where it intersects. Why doesn't it stop giving me the intersection points? Okay, I don't know why it did that. Okay, there we go. Right, so those are my intersection points, and you see that they are what you would expect. Okay, okay, jolly good. Oh my goodness, what is happening? Okay, this froze on me. Sorry for the technical difficulties. Okay, cool. Let's talk about 15. Okay, so use the graph to find the values for x when y equals to 0 for the given equation. Write your answers in the form plus nk, where nk represents the interval between successive solutions. So now we have this entire function, and technically I think we could do this by hand, but I'm not gonna make you do that by hand. I mean, even though I could, and you should try to do it, maybe. But there's a reason why we need the graph, right? So when y equals to 0 is essentially right here. It's at this line. So y equals to 0 right there and right there. So off of those solutions, x is equal to -1 and x is equal to 3. But we know how to write solutions better like that, right? Because we know that it's going to keep on repeating. So how much does it repeat by? Every what? Every 4 units. 7 plus 4. So you should write this as x is equal to -1 plus and minus 4k or 4n. No, sorry, 4k, right? Because this interval goes from 1, 2, 3, 4. There's 4 units here. Okay. Technically you could have technically written this as well as like x is equal to 3 plus and minus 4k. Yeah. Okay. That's pretty straightforward. Do I want to do it by hand? I know. I don't. Let's see why. Let's just see why we couldn't do this by hand. So if it's 0 is equal to sine of nx over 2, I want to know, plus 1. So then -1 is equal to sine of nx over 2. Oh, we couldn't do this because there's two very. Oh, that's pi. Pi x. So this is pi x, right? So then I do sine inverse. So when is sine, so I'm left with pi x over 2 is equal to sine inverse of -1. So unit circle, where is sine inverse -1? So sine is -1 down here, right? That's at 3 pi over 2. So pi over x over 2 is equal to 3 pi over 2. Now let's kind of multiply this by 2. Pi x over 2 times 3 pi equals 3 pi over 2 plus 2 pi k. And I'm multiplying this by 2. So I'm left with pi x is equal to 3 pi plus 4 pi k. And then I'm dividing this by pi. So then I'm left with x is equal to 3 plus and minus here, plus and minus 4k. Okay, so then we see that the only difference that we have is that there's a 4k, but my first x value is this 3, which is kind of where I had told you earlier that you could start at 3. Okay, that was just a little bit off of me going off on a tangent. Let's talk about 16. Use a unit circle to explain the solutions you found in problems 15. So I'm going to state that this is my solution, okay? But what does it mean? So it means that the period of the graph is what? 4, right? Because it's repeating every 4 units. The period is 4. So when x is equal to -1, y 0. So this is right there, right? And where else is, yeah, so this is -1 at 0, right? So then every single time when y equals 0, I do 4 rotations, right? So it takes a full rotation to get back to this, right? So what this means is that if 4 on the graph represents seconds, so the graph here was seconds from like, what was my x variable? It doesn't really tell you what it is. Yeah, but essentially it just means that if I have to rotate 4 times to end up back at this point, okay? My goodness, did I not click this? Sorry, as you know, I was working ahead on this because I wanted to make sure that I didn't mess up, but I forgot to clear the pages. Okay. So my period here was 4, and all this means is that it equals 0 again at x equals -1 plus 4, right? So -1, 3, 7, and so on. Okay. Okay. Now we're talking about 17. So use the graph to approximate the points of intersection of the graphs y1 and y2. So intersection points, you can see that there's right there's one point, right there's another point, and then there's another one right there. So my first point is here, and to just estimate these, it's negative pi comma 1, I would say, is my first point. I'm gonna kind of put this here. Why not? Okay. And now we're talking about this point right there. So I would say that this is 1, 2, 3, 4. Okay, so pi over 2 can be thought about as pi over 10, 5 pi over 10. So then each of these is a pi over 10. So then this right here would be 2 pi over 10 or pi over 5, comma, each of these is 1, 2, 1, 2, 3, 4, 5. So each of those would probably be 0.2. So I'm thinking that this is 2 and 1/5, which can be written as 11 over 5. So this is equal to pi over 5, 11 over 5. That's what this point would be. That's my best estimate of that. And then this point over here. So these all go by pi over 10, 5 pi over 10, 6 pi over 10. This is in the middle. So I'm gonna say this is 7 pi over 10. I won't give you something that ugly. And then this is gonna be 1/5, 2/5, 3/5, 4/5. So a little below 4/5. So that's 0.8. So let's do 2 and 3/4. Or it's equivalent to 7 pi over 10, 11 over 4. Okay, this is just kind of estimating your values. Could be a little bit off, but not so much, especially not this point over here. That point is pretty much spot on. Okay. Let's show you how to do this on the calculator just for this one. So for the fun of it, let's go to y equals, and I have 2 sine of x plus 1, enter, and I have a line 1 over 3 x, I hope I read it correctly, plus 2, graphing this. So I do see that there's some intersection points, right? I think this is my window. It's the best one to talk about. So second, calculate, go to intersect, my left bound. Let's kind of think about let's use this point. Let's find that point. My right bound is that. So my intersection is at 2.11 and then 2.706, which is pretty close to 2.75. So even I think we could even change it to like 2.7, if I'm being honest. But it's okay. 2 and 3/4 is totally fine. Let's just keep that. Okay. The scale on the x-axis on the graph of 18 is 1. The scale in the graph of problem 20 is, I don't think this is right. This is supposed to be 18. Okay. The units on both axes is radians or are radians. So label the approximate location of pi over 2 and pi. So kind of just thinking about what pi is equal to. It's 3.1415 something, right? So I'm just going to say that this right here is pi. Why not? And then pi over 2 is approximately half of 3.14, which is 1.57. So somewhere in the middle of between 1 and 2. So somewhere along here would probably be our best bet that this is pi over 2. Okay. Label the graph at the approximate location of 1, 2, and 3. That's funny. Okay, so this is pi. So then 3 has to be like a little bit before. So I'm gonna say that that's 3 right there. And then 4, this is 3.14, so then 4 should be somewhere here. What about 1 and 2? So pi over 2 is like 1.57, so then 1 is like somewhere here, I would say. And then between 1 and 3, 2 is like maybe there. Yeah, these are interesting questions. You could actually kind of like put into your calculator and kind of figure it out from there. They just want approximate locations, so I'm not going to be too picky about that. Um, yeah, okay. I hope that made some sense. There was a lot of work. Um, yeah, if you have any questions, please make sure to attend office hours. I think the moral of the story for these problems is that you need to know your unit circle. So know your unit circle. Okay. Otherwise, it's going to be incredibly challenging for you to do it. But yeah, so keep having a great rest of your day. Enjoy.